Hello everyone, this is Mohammed bin Zakta with you, and today's lecture is about multiplication of signals. In the previous video, we have taken a look at how to generate sinusoidal signals and see its representation in both time domain using a scope and the frequency domain using the spectrum analyzer. Today, we're going to take a look at how to multiply that signal with another signal of a rectangle type. So before doing that, let's take a look at how to generate rectangle waveforms. By going to the library browser and searching for rectangular, we're gonna drag the rectangular waveform box to the workspace. There's an easier way. Instead of each time going to the library browser and searching for the box and then dragging it, we can left click in any of the empty space in the workplace by just one time, left clicking one time and then typing the thing that we want. For example, let's type in scope and pressing enter, we will have a scope ready to be used. The same thing, one left click in the empty space and then let's write spectrum. We don't have to complete the word, it's gonna give us some suggestions. For example, here spectrum analyzer, we're gonna choose it and then we're gonna drag it. Now let's connect these together. Before going deep into the parameters of a rectangle waveform, let's take a look at the rectangle signal. A rectangle signal is represented by this form, x of t. It always depends on what is known as tau. This tau here means the pulse width. This is the width of the rectangle signal. So here pulse width over 2, tau over 2, 2 minus tau over 2 gives us the pulse width tau. So after opening the rectangular waveform, we're going to choose for pulse width, this is tau. Let's say for example 0.1 seconds, and the sampling rate, it's the represents the sampling frequency. Let's choose 2000. Pulse repetition frequency, this helps us to determine the pulse repetition interval. Since the pulse repetition interval is equal to 1 over pulse repetition frequency, let's choose a pulse repetition frequency to be 1 Hertz, for example. This means our pulse repetition interval is going to be 1 second, 1 over 1, which gives you 1 second. This means that our generator gonna regenerate the rectangular waveform again after 1 second with the same parameters, with the same pulse width of being 0.1. So each 1 second we're gonna have a rectangular signal with a pulse width of 0.1. This will represent a pulse train. So we're gonna press OK. Before simulating our workplace, there's an important note here. In the scope, we're gonna go to settings, and input processing should be frame based. Input processing should be frame based. Now after finishing that, we are ready to simulate. This is the results of the spectrum analyzer. We're going to take a look at it later on. Let's take a look at the scope. Here, as we can see that, let's zoom in. This is our rectangular signal. This is our rectangular signal with a pulse width of 0.1, from 1.1 to 1, which gives you a pulse width of 0.1 as we have given it in the parameters. And also by going back, we can see here that it repeats itself every 1 second. This is due to the pulse repetition frequency, which is 1 Hertz, and since the pulse repetition interval is 1 over PRF, which is pulse repetition frequency, this means that our interval is 1 second. So here at 0, and then it repeats itself at 1, and then at 2, and like that. There's another note as well. Let's zoom out. Here it stopped at 10. That's because we have given 10 to be our maximum value in display from here. So since our maximum display value is 10, it stopped at 10. So this is the representation of the rectangular form in the time domain. In the frequency domain, we're supposed to see a sinc function. This doesn't look quite well as a sinc function. This is due to the sampling rate that we have chosen. It's not smooth. So in order to make it smoother, we're gonna go to the rectangular waveform and we're gonna choose sample rate of 1000. By choosing the sampling rate of 1000 and simulating it again, we can see that here from tools, from tools, automatic scale limits, we can see here that this is a well-known sinc structure. With this is the first zero. What the value is supposed to be is 10, because the first zero is 1 over pulse width, which means 1 over 0.1, which gives us 10 hertz. So we can see here that the first zero is at 10. Now, after learning how to generate the rectangular waveform and how it looks, how does it look like in the both time domain and frequency domain, let's multiply it to a sinusoidal function. Let's delete these connections. This is a rectangular. Let's add a sine wave of type DSB. Sine wave DSB system. This is our DSB sine wave, and we're going to add a product. We're going to do the connections. Here, in this example, I would like to represent a new thing. Instead of using a spectrum analyzer, we're going to use something known as a vector scope. A vector scope shows us the signal in the time domain or frequency domain as we desire. Spectrum analyzer always shows us in the frequency domain. The spectrum analyzer has a hidden Fourier fast transform inside it. So in order to use a vector scope, we have to use the FFT function, which stands for fast Fourier transform, and then take its absolute value by using the box of ABS, absolute value of that Fourier transform. So here, by taking the fast Fourier transform of the signal and by taking its absolute value and then by using the vector scope, we're gonna have the same result as obtained from the spectrum analyzer. Spectrum analyzer is usually used because it is easier. So instead of having these three boxes, these three are equivalent to the spectrum analyzer. But focus here, this is time. We have to double click on the vector scope and we're gonna choose frequency. Also the axis properties, instead of 0 to the sampling frequency over 2, it should be minus to positive. It's going to have a wide range. With this can be, let's increase this to minus 30 to 30 to show us the complete signal after simulating. So now this is changed to frequency. The vector scope is ready to work as a spectrum analyzing by the help of the absolute value and the fast Fourier transform. So now the sine wave, let's give the parameters of the sine wave. Let's choose the amplitude to be 1, a frequency of 50 for example. This is the important part here. The sampling time should be the sample per frame should be equal to the sample rate. So for example, if we choose here 2000, the sample per frame should be 2000 as well. So the sample per frame is So 2000, and the sample rate is 2000 also here. Instead of restarting at time 0, we're going to catch up with the simulation time for better results, and we're going to see are they equal or not by going to display and signal sandboards. After that, signal dimension. Since a signal is like an array, in order to product these signals, they have to have the same dimensions. So the dimension of the rectangular waveform is 2000 multiplied by 1, 2000 multiplied by 1, which is the same as the sine wave 2000 by 1. So since they are equal, we can product them. Otherwise, this production cannot be obtained. So in order to product any two signals, their size should be similar. Also in the fast Fourier transform, instead of FFT length should be equal to the sampling rate as well. So it should be equal to 2000. Now, after giving our sine wave and the rectangular, everything is ready to be simulated. What are we going to what is expected from this results? Well, a sine wave or a cosine, its Fourier transform is simply two pulses depending on the frequency itself. For example, in this situation here, the frequency is S. So the two pulses are going to have to be one positive, one negative, with the same value of S. Just shift to the right by the value of S and shift to the left by the value of S. Similar to the sine function, shifted to the right by S and shifted to the left by S. So when we take the Fourier transform of these two signals and we multiply them to each other, the result is going to be simple multiplication. We know that the rectangular function, in terms of its frequency domain, it is equal to a sinc function. So this means that sinc function, instead of being at the origin, it's going to be shifted to the right by the value of the frequency of the sine wave and shifted to the left by the value of the sine wave frequency as well. Again, instead of having the sinc function in the origin, after multiplying the rectangular signal to the sine signal in the frequency domain, this sinc will be shifted to the right and to the left by the value of the frequency that has been determined. So in here, since our frequency is 100, for example, let's choose 50 as we said. This means that our sinc is going to be shifted to the right by 50 and shifted to the left by 50 as well. In terms of the time domain, the rectangular, instead of having a continuous sinusoidal function, is going to be limited to the width of the rectangular. So since our frequency is 50, this means our period is 1 over 50, which gives us 0.02, and our rectangular pulse width is 0.1. This means each rectangle with a width of 0.1 is going to have 5 sinusoidal periods. That's because 0.1 divided by 0.02 will give us 5 periods. Again, instead of having a continuous sine wave, in multiplying it with a rectangle, the results in the time domain is going to be 5 periods in each rectangle width. That's because the period is 1 over 50, which is 0.2, and the pulse width is 0.1. So after dividing 0.1 by 0.02, we're going to have 5 periods. Now let's take a look at these results. Here, let's start with the time domain first. This is our rectangle pulse train, as in the previous example, 10 seconds, each width a 0.1. Let's zoom in. We can see that here that we have two types of sinusoidal. One in two different colors. This is due to the complex sinusoidal part. So to have just one, let's go to the sine wave and choose the output complexity to be real instead of complex. This will show us only the real part. So running it again, let's close this and open the scope. This is our rectangular train again. Let's zoom in here. After zooming, let's go to view, the tools, axis scaling, automatic scale. We can see here that our pulse train, our pulse width is 0.1, same, including a sine wave inside it. This is due to the multiplication of sine and rectangle in the time domain. So when we multiply sine wave to a rectangular wave in the time domain, we're gonna obtain this waveform here. This waveform in each sorry, the computer just hang for a minute. Let's close it. I also have a note here. Discrete, real, 1 over 1000, 1 over 2000. Okay. Let's run it again. Also, there is a small thing that we have forgotten here. The sample time should be 1 over the same as the samples per frame. So here it should be 2000. Now after we run it, just should close this one. In the scope, here in the pulse width, we can see that in each 0.1 pulse width, there is going to be 5 sinusoidal functions as mentioned. So this is 1 period, 2 period, 3, 4, and 5. 5 periods, 5 sinusoidal periods, which is 0.02 each, with a pulse width of 1.1 here in the rectangle pulse width. Now let's take a look at how they look like in the frequency domain. 1 second. In the frequency domain, we can see that two sinks have been shifted. Instead of having just one sink in the origin, they have been shifted to the right and to the left with a frequency which is equal to the sinusoidal frequency. Here it's 0.05 kilohertz, which means 50 hertz. The sink function is shifted to the right by 50 hertz and shifted to the left by 50 hertz as well. This is due to the sine wave 50 hertz here. Let's take a look at the frequency axis. Evidence. I don't know why it's not this. Here. This is the spectrum. Let's run it again. This is the vector scope. The vector scope shows us two sinks. This is the sinks here again at 0.05 kilohertz and minus 0.05 kilohertz, which is equal to 50 hertz. We have proven that the spectrum analyzer and the vector scope shows us similar results, as being the frequency shifted to 0.05 and minus 0.05. So we notice that the spectrum analyzer has a Fourier fast transform built in inside it, and as well as taking the absolute value of that transform. So in conclusion, a rectangular signal by itself gives us a sinc function in the frequency domain, and a sine wave by itself gives us two pulses shifted by the frequency of that sine wave. So when we multiply a rectangular with a sine wave, our result is going to be, by this we can see here that this sinc wave is not smooth. So again, all we have to do is just change this 2000 to 1000 to make it smoother. If we change this means we're going to change the sine wave as well. 1000 here, and the Fourier transform is going to be 1000. Let's simulate it. This is 1000. This should be 1000, 1000, 1000. So all of them are the same. Here, this is 1000 as well. So let's run it. So as a rectangular multiplier to a sinusoidal gives us two sincs shifted by the value here 50 Hertz. That's the conclusion of this video. I hope that you enjoyed it. Thank you for your listening. I hope to see you in another lecture.